in. So where we ended last week was pretty much at the slide. I think we went a little bit further. But kind of the ultimate goal of last week was to go through and look at the individual energy levels. Okay, and that's what Bohr ended up finding out by seeing the line spectra, the atomic spectra. Okay? So what happened there is he saw transitions between discrete energy levels, which meant that we had to have some kind of energy level system built into this. What we're then able to further refine is that there ended up being subdivisions within those energy levels, and we ended up with types of orbitals. So at our first breakdown, as we move up an energy level, we get an extra orbital type. Okay? Turned out, though we haven't quite covered that yet, that there's also something known as the orbital orientation. So when we generate a new orbital type, there's multiple ways that orbital can be oriented in space, which means we get more potential orbitals. Okay? The very last thing, which we won't worry about too much, is the electron spin, which ultimately says or summarizes for us that 2 electrons can exist in every orbital. Okay? So that was kind of our goal at the end of that. And then while that can be confusing, try and relate it back to something reasonable. It's looking at an address on where they live. So ultimately a state, a city, a street, and an address. So how do you zoom in to figure out exactly where that electron is located? Okay? So orbital types. We end up with 3 possible orbital types. And you'll typically see these shapes associated with these orbital types. These come from a derivation of Schrödinger's wave equations, which is something way beyond even I could do reasonably. I saw it derived once where they went, look, this number means this. Here you have a sphere. This number means this. Oh, now it's a dumbbell. Okay? So it's really neat to see, but you need massive amounts of mathematics and understanding behind that, very little of which do I own. Okay? If you can own knowledge, that is. So as far as what these shapes are, is it's a 95% probability of finding the electron, okay, which is kind of an odd thing to say. The electrons, if we look at some pictures, you say, oh, we have these little circles around our nucleus, and the electrons just move around in a circle. Well, that's not really the case. Electrons can skip and dance wherever the heck they want. Okay? They can be in one position at 1 second, and in the very next instant can be somewhere across the atom. Okay? So what these are orbital images coming up with a prediction on where the electron is going to exist. It can potentially exist outside of these ranges, but it's very unlikely for it to be there. Okay, so these are what are referred to as probability maps. Within those probability maps, you end up with these general shapes and appearances behind them. Okay, we could go through and memorize these based on what they look like. For that first one we've got, what does that look like to you? We've got a sphere. Next one, already heard me refer to it, dumbbell. And the last one, 4-leaf clover is too much work, so I'm just going to write a clover leaf. Okay. Scientists don't like words as much as they don't like numbers, okay, or chemists don't, at least, which you've clearly seen with my ability to spell and speak in many cases. So we want to come up with an abbreviated symbol for each of these. Instead of referring to them as sphere, dumbbell, and cloverleaf, we can call them, do the reading. Sphere begins with S. Dumbbell begins with, in German, dumbbell begins with P. Cloverleaf begins with D. Again, in German, it begins with D. If you believe that, don't. That's a bad thing to believe. Okay? We came up with S, P, and D for these. Okay? Those are true. I didn't make those up. So those are the names that we can refer to these elements by. We can look at them as the individual shapes on what they appear as, or we can refer to them as their letter code. Most people will refer to them as the letter code, and we'll end up using the letter code more frequently. Any ideas why we might use the letter code more frequently? It's easier. That's about it. Okay, there was a hand. Is it you, Troy? No. So remember, as you go up in energy levels, you add a new orbital type. So if we go through and look at this, if we start at the 1 energy level, we start with S. Okay? Any ideas why we'd start with the S and not, say, the P or the D? It's the simplest. Okay? Your S shape is the most simple of all of them. Okay? Lowest in energy. Everything strives for neutrality. Everything strives for simple before we make it more difficult. So we start at the S. When we move up to the 2nd energy level, we're still going to have an S-type orbital. Okay, it's now just going to be at a higher energy. But remember, as we move up in energy level, we also get an extra orbital type. That new orbital type happens to be P. So when we move up in energy, so now I'm going to go back here real quickly. In our black state at the very bottom, our lowest energy, the only orbital we've got is the S orbital. Hey, let's color code, why not? When we increase in energy, move up to the 2nd energy shell, we still have the S orbital as a possibility. But we add an extra type. That extra type is the P. What happens when we move up in energy level again? Okay. We're still going to have all of the potential types that we had underneath, so we will have S and P. Sorry, that green's kind of faint. But we have an extra energy, or an extra orbital type. What's that extra orbital type? D. If we move up in energy yet again, ooh, yellow's a bad color, let's call it orange. We will have S, we will have P, we have D, but we moved up in energy, right? So we get another orbital type. What's the next orbital type? F. Okay, why S, P, D, and F? I have no idea. Okay, go to the textbook to figure that one out. Maybe they'll tell you, though I kind of doubt it. Okay? So as you move up in energy, you increase the amount of potential orbitals that you can work with. Each of those, got to be a little bit careful with that. Each single orbital can hold 2 electrons. Okay? But remember, not only do we increase the number of orbital types, but we also have the potential for increasing our orbital orientations, which we haven't talked about yet. Okay, so let's go back to our shapes and now move to our orbital orientation. What orbital are we showing here? We have the S orbital. Okay. How many S orbitals are possible according to our periodic table? So this is an interesting question. It can be helpful with our periodic table. We've actually addressed some information here. If we go to the lowest energy, where's our lowest energy? Which element? Turns out to be our highest element. With the S orbital, how many electrons can we, well, sorry, first, how many orientations are there as I hold up the answer? It's only 1 orientation. Well, what do I mean by that? If we take a sphere and I turn it, what does it look like? Sphere. We don't see any difference in that overall shape. It still looks like a sphere. Okay? How many electrons can I put in that one possible orientation? 2. Okay? So we can start with hydrogen. If I wanted to describe the electron configuration around hydrogen, we could start off with, first off, being lazy. Could write our symbol, H for hydrogen. And we now want to put our electrons around it. What orbital are we going to put the electron into? Put it in the S first. Which energy level is that? Our lowest. Let's give us a number to our lowest energy level. 1, our first energy level. Okay. When we look at hydrogen, how many electrons does it have? 1. How do we know that? Protons and electrons. Okay, so a single hydrogen atom only has 1 electron. We now want to add to our notation where that electron is, that it's part of that orbital. Where could we specify that? There's all sorts of options. Okay, We could try and use a subscript. We did that when we looked at formulas, right? If we had ammonia, NH3, what did that 3 mean? There were 3 hydrogens. So we could go through and use that same general idea with our electron configurations. What's the problem with that going to be? What did I just write?
It looks like
I wrote 1s3, but what's the issue with s? It's a symbol for sulfur. Did I really write 1s3 or did I write sulfur 3? Okay, that's a bit questionable. So we don't want to use a subscript. What if we put the number out front?
31.
Now we potentially get 31. So that doesn't work either. We'll go to the top. Upper right-hand, whoops, how many electrons we put in there? We only put 1 electron in, right, for hydrogen? So 1s1, there is a single electron in the 1s orbital. What happens when we add an electron? And a proton, technically. We change the element to helium. So now instead of it being, what do I want? Hydrogen, I would have helium. What would my electron configuration for helium then look like? 1s, but I have an extra electron. Where do I want to put that extra electron? I've got all sorts of options for here. Right, 1s1, right? Okay, why would we not do that? Okay, we've got a couple interpretations. First off, I would say that's too much work. We're having to write the same orbital multiple times. That's a bit tedious. Okay. The next issue is that this 1 electron, our orange, well, I guess it's orange in both cases. So let's fix that. Our orange 1 electron is in the same orbital as our black 1 electron. Why did we draw them as separate entities then? Well, it doesn't really make any sense. If we draw them out as separate entities, that can get confusing. So what we can do instead is write it out as 1s2. Okay? Questions about that so far? Because it only gets more complex. Okay? What happens when we add another proton and another electron? Let's move up to the next element. What element would that be? Lithium. Okay, we first off are going to have our 1s orbital. How many electrons can we put into that 1s orbital? We can only put 2 electrons into any given orbital. Okay, but this brings up an issue. How many different orbitals did I have at that first energy level?
2.
1 orbital with 2 electrons that can go into it. Lithium has a 3rd electron. Where does that 3rd electron go? It's going to have to go to the next highest energy. How do we specify our next highest energy? We bring in our 2. What's our lowest energy? Our 2s orbital. Okay. How many electrons need to go into that orbital? 1, 2s, 1. We've now accounted for the electron configuration for lithium. What happens when we move to sodium? We're going to have to shift in energy again. And potassium? Again. Where are our energy levels denoted on the periodic table? Every row is a new energy level. Okay? So we've got that information stashed in our periodic table. You'll notice that the only ones that I picked to discuss at this point were in that first column. Okay? We could even shift to the second column, but I don't want to shift beyond that because that's going to make it a little bit more complex. Okay? What do I mean by that? Let's shift to boron. We make this boron now. How many electrons need to go into boron? 5. So if we go through and take a look, we start with our 1s, 2 electrons into that lowest energy shell. How many electrons need to go into our 2s? 2. So we can adjust that here real quickly. But I can only fit 2 electrons into the 2s. I need 1 more electron position. So we could jump to the 3s, but remember from our previous diagram, as we increase in an energy level, what do we get? We get a new orbital for that energy level. What was that new orbital for our second energy level? Our p orbitals. That p orbital is going to be preceded by the 2. Why the 2? Because it came from our second energy level. Okay, it's in that second row. Okay, how many electrons need to go into that for boron? 1. What happens if we jump up to, say, nitrogen? One S2, 2s2 gets us how many electrons? 4. Our boron gets us 5. How many electrons can that 2p orbital hold? So this is where our confusion shows up. I asked for the orbital. How many electrons can fit in an orbital? 2. Why is that a problem? If I can only put 2 electrons into the 2p orbital, I can't get to nitrogen without moving to a new energy level. This is where the orientation comes into play. With the s orbital, there was only one orientation, a sphere. We only ended up with that one s orbital. That's all we could get. Okay, 1 being a number in that case. Okay? When we move to the p orbitals, one of the standard ways to draw it is as such, right along the x-axis. What happens if I turn that by 90 degrees? Would you be able to tell me that that looked different? Yeah, one case it's running this direction, the other case it's running up and down. Okay? What if I turned it another 90 degrees, but now towards you? Does it also look different? Yeah. So what happens with our 2p orbitals, and this is what they're attempting to show in this, which is a lot nicer than I can draw, is that we get 3 possible orientations. Okay? We can add extra information to these and refer to this one as the 2px. Why x? The orbital's on the x-axis. The next one would be the 2p. Why? Because the orbital's on the y-axis. Last one, 2pz, because it's on the z-axis. So if we go through and try and draw out our nitrogen, what am I trying to draw? Nitrogen, right? We've got our 1s2, 2s2, and then we could go through and say 2px, 2, whoops, that's a p, y, 2pz, to specify all of those extra orbitals. Okay? When we go through and fill, we always fill lowest energy first. So when we start, we could go with 1, 2, 3. Wait, 3? Does that get us 7? That gets us 7. There we are. So we could call nitrogen 1s2, 2s2, 2px1, 2py1, 2pz1. Okay? So what we've done is actually split apart those orbitals into the individual orbital orientations so that we can see those orbitals. You'll notice the textbook doesn't do it this way. Okay? The one thing that they do is they say, well, these are all 2p's. I don't care what axis they are on. They're all 2p orbitals. So what they do instead is say, okay, well, I'm going to condense that information or summarize it into being 2p3. Okay? So it appears that the p orbital can hold more. No, the orbital class can hold more electrons, but that's only because there's more orbitals within the p class. Okay? So if we go through and look at the capacity for the p orbitals, what's our capacity? 6 electrons. So let's go through and evaluate what happens. Okay, so lithium was, sorry, I have short attention span. 2s1, beryllium, 2s2, boron, 2s2, 2p1, carbon. We'll skip the s, 2p2, nitrogen, 2p3. What happens when I need to add another electron? By shifting to sodium. I go up to the 3 energy level. Now I start at 3s.
Oh, what about D and F?
Okay. Do we have... Sorry, now I got to go back twice. Now I got to go back like 3 or 4 times. Do we have D and F at the 2 energy level? No. Okay. We only classify up to the P. We haven't increased in energy enough to get more orbital types. Okay. So far, kind of. Okay, because really, it's only going to get worse. So if you've got a question, you need to ask. Yeah.
When we start doing these, are you going to ask us to specify P, X, X, Y, and Z, or are we just going to do...
No. I won't ask you to specify P, X, Y, and Z. I'll ask you to summarize based on the orbital as a group.
Because on the P level, like when you add more orbitals, the electrons can jump the orbitals, right? So they can get into different orbitals.
We'll avoid jumping for the moment. Let's try and keep it simple.
So based on the periodic table, there's 7 energy levels?
So if we go back to the question that I asked, how many energy levels were in the periodic table? Hydrogen starts us at 1, lithium, 2, sodium, potassium, rubidium, cesium, francium. How many possible orbital types for francium? We add 1 every time we move up an energy level, right? So when we moved from 1 to 2, we had 2 possible orbital types. When we move to 3, how many orbital types do we get? 3. When we move to 4, how many orbital types do we get? 4. So when we get to the 7th energy level, how many orbital types do we have? 7 orbital types. Okay. Do we fill all of those orbital types? We have the potential to, but we don't. Okay. Why do we not fill them? What happens as we get further away from the nucleus? What did we say was our maximum energy level? The electron not being part of the atom. As we get further away from the nucleus, eventually the atom gets so massive that the electrons aren't attached to the nucleus. Okay? Aren't attached to the atom and free float off into nothingness. So we have kind of a maximum limit as far as atomic size goes. In theory, we could keep adding electrons in. But eventually, we make the atom so large that the electrons out on the outside just aren't attracted to the nucleus. So what happens to them? Our atom falls apart, the electrons go somewhere else. Okay, and there's other things that contribute. We also have nuclear issues. If we get big enough, the nucleus falls apart as well. Becca, you had a question.
At first I was just confused, like, why, I thought the blue one was the first one, but
Nope,
it's
yeah.
the black one,
The black one's your first energy level.
which only has S and then SP and then SPB.
Yep. All right. Other questions on that? Paul, you had a pseudo question, it looked like. No? So we also, when we looked at our possible orbital types, you notice I went up to D. Okay? So what happens when we get to the D orbitals? Well, that D orbital, as easy as it is to see, is kind of sandwiched between a couple different axes. Okay? We can get multiple different orientations for the D orbitals. Those orientations, we get 5 possible orientations, and these are the shapes. You'll notice we also get one extra weird one. Okay? That's because if you close your eyes and kind of blink really fast, that last weird one looks a lot like the other ones combined. It's a mathematical issue. It falls out of the mathematics. Our interpretations of these orientations only work so far before eventually we're going to run out of possible ways to wrap our brains around that concept, and it just becomes complete loss. Okay? What do you need to get out of this information? Number one, you need to be aware of the individual shapes and what results from those orientations. The ones I'm primarily concerned about would be the S, P, and the D. For your S orbitals, how many orientations do you get? 1. For your P orbitals. 3. For your D orbitals. 5. Okay. Can we add more orbital types? Absolutely. Okay. The next big orbital type that actually gets filled is the F orbitals. Okay. Or has the potential to get filled. I don't even have pictures of those. Okay. Maybe because I don't really want to look at them either. Okay. Sorry, do you want that back? Do you want a question?
Do we have to memorize the different orbital types?
You have to realize, as far as the orbital types, how many there are per orbital class. Or sorry, orbital types, yes.
We don't
Yeah.
need to know what they look like.
You need to know that the S orbitals look like spheres. P orbitals look like dumbbells. The D orbitals, for the most part, look like clover leaves. Okay. Beyond that, you don't need to know anything else as far as the orbital types. Orbital orientations. What do you need to know for the orbital orientations? How many orientations are there for an S orbital? 1 for a P orbital. 3 for a D orbital. 5. You don't necessarily need to know how they look. Okay? But for the most part, you got that out of the shapes. Okay? I could be mean and on the test give you this image and say which orbital type does it classify to. Okay? We've talked about 3 orbital types. The S, which looked like spheres. Is that a sphere? No. The P, which were dumbbells. Kind of looks like a dumbbell, but it's got a donut on it. So that's not a P. Well, as far as our classifications, though, if it's not S and it's not P, it's D. Okay? There's a reason I haven't shown you the F. Okay? So it can be easy to get lost in what's going on with those. Simplify it down to those basics. What types of orbitals do we have? How many possible orientations? You're ultimately responsible for the numbers of them, not so much how we're deriving them or even what axes they're on. Okay? Yes?
For each one of the Ds have only 2?
Every orbital holds 2 electrons. Okay? So if we look at an S orbital, how many electrons can we get into the S class? How many electrons can we get into the P class? Sorry, 2 electrons. 6 electrons into the P class. How many electrons can we get into the D class? 10. Okay. If you move to the F class, we could figure that one out by using the periodic table, and we'll come to that in a second. Okay. So what this means to us is effectively what we've got here. I've gone through and with that old diagram that we had, went through and added each of the possible orbitals. Okay. We will always add electrons to the lowest energy first. So we always start at the 1 and work our way to higher energy levels. Okay? Before we jump to a higher energy level, we want to pair it. Okay? So when we did the 2s for nitrogen, we put our 2 electrons into our s orbitals first. Then when we jumped to the higher energy level, okay, we had to first off pair the electrons in our s. Jump to the higher energy orbital and we put an electron in. Where did the next electron go? Into the next p orbital. Why would it go into the next p orbital and not the same one? We aren't jumping in energy. Okay? So we will fill half first then double back and repeat, okay, if we have to. Okay? We will look at some examples here, actually kind of on the, well, no, this is more of a summary slide. Okay? So how many electrons can go into our s orbital, our energy level 1? We can only fit 2 electrons in there. Okay, so our electrons per sublevel and our electrons per energy level comes out at exactly 2. What happens when we move up to an energy level of 2? Our energy level is now 2. What's our energy sublevels? 2s. Is it only 2s? I like the shaking of the head, no. Is there another energy level? Is there another sublevel or another orbital type that happens when we move up in energy? We get the 2p. How many electrons can go into the 2s? 2. How many electrons can go into our p class? 6 electrons, because we get those 3 orientations. What's the electrons per our energy level now? We can get a total of 8 electrons in the second energy level. Okay? We could jump to the 3 and the 4 and the 5 and so on and try and add those electrons in. I'm not sure. Hey, good. Did exactly the same. Okay? So we could jump up to the 3 energy level. We've got now our s and our p's, but because we've increased in energy, we also get a new orbital type or sublevel. So there's D. With our 3s, it's still 2 electrons. With our p, still 6 electrons. With our d, 10 electrons. Whoops, I pointed the wrong one. Total, what do we get within that energy level? 18. What we're doing is summing everything with that 3. We could jump to the 4, and that's where we get our 4f, and we can start getting more electrons into these. Okay? So we could memorize all of this information. Let's make sure I'm on the, oh, what slide I'm, no, still on that kind of memorize thing. We can look at an electron diagram for filling orbitals. We could start at the 1s, and then we can just move up, 2s, 2p. And so the idea is that you would draw this little diagram, starting with your 1s at the bottom, next row 2s, 2p, 3s, 3p, 3d. And then we go through to fill, and that's what the arrows are supposed to show. Go diagonal and fill along that diagonal. That's the intent of this diagram. So we could go through and attempt that. So what we're going to go through and do is do that here. One of the things that we want to be able to pull out of this is the electron configurations. So let's take a look at carbon, because carbon's my favorite. Was that a yay? Okay, I can accept a question on that. I guess it wasn't a yay. Yeah, go ahead.
So if the 1s has 2 electrons and the 2s has 2 electrons, wouldn't it be 10 electrons when you get to the 2p?
When you get to the 2p within the 2 energy level, so those totals were only per energy level. Within the 2 energy level, you only get 8 electrons. The total electrons that we've put in by that point would also include everything underneath it. And that's not what that previous slide showed. It only said per energy level. All right. So we're going to generate our electron configuration for carbon. How do we start? Usually a nice good place to start would be a symbol for what carbon is. Okay. How many electrons do we need to get into carbon? Sorry, I decided to do some other things. We need 6 electrons in there. The notation I'll use for electrons is E minus. Why E minus? E stands for electron. The minus stands for its charge. Why else do I use E minus? It's less work than writing electron. Okay, so let's start off with our notation. We start with carbon. Okay, if we've got our filling diagram set up, what's the first orbital we start with? Our 1s. How many electrons can fit into our 1s? 2 electrons. Okay? Have we put in all the electrons that carbon needs? Nope. So what do? Move to the next energy level, our 2s. How many electrons fit in the 2s? 2. Have we satisfied all of the electrons that carbon needs? No. So what do? We'll go to the 2p. How many electrons need to go in our p orbitals? We need 2. Have we put in all of the electrons that carbon needs? Yes. We now have the electron configuration for carbon. Okay? Really not horrible. I mean, it seems like an awful lot of stuff, but it isn't too bad. And we're going to look at another pattern that can simplify it in a second. Yeah. We'll do another example for that. Okay. Before I do that other example, I want to address the idea of valence electrons. What is happening with valence electrons? Okay, one of the next topics we're going to move to is chemical bonding. Okay, chemical bonding means we take two atoms and we bring them near each other. Eventually, they start to interact with each other and permanently stay attached, okay, until we chemically rip them apart. Okay? What's going to cause them to stay attached? What's the first thing that's going to interact between those two atoms? The electrons, and it's going to be the electrons furthest away from the nucleus. So our highest energy electrons. If we go through and take a look at these, which are our highest energy electrons? We've got a couple different options here. We could jump up to the p, but how much of a difference was there in energy from our p to our s? Okay, we could even use the diagram here. As we moved up in energy, right? Tick, tick. What's the difference in energy between our s and our p? They're effectively the same energy. It's why they're at the same line on that axis. So when we are looking at our valence electrons, what we're concerned about is the energy level, our highest energy level. Our energy level is represented by the number in front. Okay, these are all our energy levels, right? If I want the valence electrons, I want the electrons that are at the highest energy level. Here are my valence. Okay? Those are my highest energy electrons. Okay, well, if I'm only selecting some electrons, it might be nice so that the other electrons don't get jealous. What name do we want to give to the electrons not our valence electrons? As a hint, they're located in the center. They aren't nuclear because that means they're in the actual nucleus. Our electrons never make it into the nucleus. The center of an apple, we have the core electrons. Okay? An extra notation that we can come up with. Okay? For carbon, it's not that big of a deal because it didn't take us that long to draw it out. Okay? But if we get up into, say, cadmium or iodine, trying to draw the electron configuration for those elements, you got to account for 53 electrons. That's going to be a lot of electron configurations. So what we might do is abbreviate and say, I don't want to write out the core electrons because the core electrons for everything underneath it are effectively the same, right? So we can simplify. What element has the electron configuration 1s2? Helium. So instead of writing out carbon as this big long thing, I can abbreviate it to be carbon is equal to the configuration for helium plus some more electrons. Okay? You'll notice for carbon, that's a bit silly to go through and do that. Why? The effort to write 1s2 versus bracket helium n bracket, relatively the same. So it doesn't really make sense to do it for carbon. But remember, as you get bigger, you may actually want to start using that notation. Okay? So let's pick one a little bit bigger. Let's go to, I don't want to go too far into it. Let's pick chlorine. Okay, for chlorine, what do we start with?
We have 17.
We have 17 electrons that we have to account for. What's the next thing we start with? I think someone said it there, our symbol. All right, let's be tedious and draw it out long ways first. We're going to start with 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Did that relatively fast, and I did use a shortcut that I'll show you here in a second. But what we're doing is ultimately just adding our electrons into the capacity for each of the lower energies and adding that up. If I did that right, when we total that, it should work. 2 and 2 is 4, 4 plus 6, 10, 2 and 5, 7, 10 and 7, 17. We're there. Yes, Becca.
Why does the FP and S for the two are in the same axis thing? Or why does the P have a 6 and the S have a 2?
How many electrons go into each of those? So the numbers up top, okay, our numbers, which I'll go through in circle here, refer to the number of electrons that we can put into that orbital type. Okay. The S had one possible orientation, which meant one orbital, 2 electrons. The P was the dumbbell shape. How many possible orientations could we get? 3 possible orientations. Each orientation gets 2 electrons. So when we go to fill the P, we want to put in as many electrons as we can before we jump to the next energy level. With 3 orientations and 2 electrons per, how many electrons can we put in? 2 times 3. There's our 6. Does that make sense? Does that answer your question there?
See how you put like helium in parentheses?
Yep.
Can't you put neon?
I'm about to do that right now. Other questions? Yeah.
So 2p6, if we put 2p4, is that possible? Can we do another 2p2?
So is it possible, if I can get your attention real quickly, could we say instead 2p4 and put those 2 electrons somewhere else? Is it physically possible? Yes. That's how we get our atomic line spectra, is we end up exciting electrons to higher energies and we watch them relax back down. Are we dealing with excited states here? No. Why not? Because if you thought this was confusing, now say that the electrons can go anywhere they want. Okay? That's going to make your life a living hell. What we're trying to deal with through electron configurations, we always set it up so that the electrons go into the lowest energy first, every single time. Okay? I think I saw another hand. Yes? So the intent on this diagram is to show our filling. So we organize all of our orbitals. And to fill, we start from right to left and we move up 1s and we double back. So it's like we're weaving through it. 2s and then we double back. 2p3s, double back all the way.
So what is the orientation? Orbital orientation?
The orientation tells us how many 2p's there are. How many 2p's are there? There are 3 orientations for the 2p. We're not specifying each of those orbitals because that defeats the purpose of the diagram. That puts too much complexity into it. What we want is to realize for a 2p orbital, excuse me, I am talking. For the 2p orbital, how many orientations are there? 3. So when we look at this 2p, that 2p represents 3 orbitals. Before we can jump up to the next energy level, we must fill all 3 of those orbitals. Okay. I'm not a fan of the diagram either. Okay. So what I think you're trying to do is shove too much information into this. Don't. A p orbital fits how many electrons? The p type. 6 electrons, period. It's because of the 3 orientations. A d type of orbital fits how many electrons? 10 electrons, there are 5 orbitals.
Because I cannot relate to like
1 before the S and then 2 before the S.
What energy level is this one? First energy level. What number do we put in front of the S?
Oh, the first.
First energy level. What happens once we fill the first energy level? We move up to the second energy level. 2s. What happens when we fill our second energy level? Move up to the third energy level. There are 3s. So the numbers in front are always referring to the energy level.
Then you go to the P before we go to the S.
Within an energy level, S, then P. S, then P. You always fill the S first. Within an energy level. So that might be the issue that you're doing. And you can talk to me after class about this. You're trying to fill all of the S first, then all of the P, then all. No. S, within your energy level, it always goes S, P, D. At the energy level 1, how many orbital types are there? 1. What orbital type is that?
Sphere.
S. Done. Energy level 2, what orbital types are there? Sphere, S, and P. So when we fill, we'll fill the S first. What's the next orbital that this diagram shows you fill? P. Okay, always S then P. Yes?
Why does it jump from 3P to 4S rather than 3D?
It has to do with the energy levels of how you end up filling this. So when you shift upwards on that diagram, it turns out that as we add that extra energy level, that D starts to get very close in energy to the S. Okay, so there's another level of complexity that thankfully we don't have to worry about as long as you remember to fill in this order. Okay. Writing all of that out can be a lot of work, so we can abbreviate that. The 2 energy level and our 1 energy level are full all the way. What element matches our 1 and 2 energy levels? Neon. So what we can say is that this is neon 3s2, 3p5. We've just added those extra electrons to that class. Okay? So how can we decide what element to use for our shortened electron configuration? It's always our noble gas preceding it. Okay, so when we look at chlorine, what's the noble gas that precedes it? Argon follows it. What precedes chlorine? Is it sulfur? Are any of these noble gases? Nope. So turn the periodic table into a cylinder. What happens? We go all the way across, move up to the previous energy level. There's our neon configuration. Right, so you can shorten your notation by looking at that electron configuration. Yes?
So you have to use a noble gas. How come we couldn't use magnesium and then just put...
The reason behind why we use the noble gases comes back to a couple different reasons, or a couple thoughts of logic on it. Primarily, we're looking at the core electrons, so that's going to be your easiest reference. If we use just sulfur in the case of chlorine, what ends up happening is, first off, we can't cut that off. The difference between sulfur and chlorine is 1 p electron. What's the notation that you're going to use? Okay, it would look really, really odd. Okay, you'd say sulfur plus an extra electron. It just seems a bit odd. Remember, when we're dealing with bonding, what are we looking at? We're looking at how the valence electrons interact. What electrons are the valence electrons in chlorine? Those 3s. So we always want to have those at hand because those electrons are going to explain the bonding later on. Okay, so we always want to be able to see those in both cases. So when we jump to our electron configurations, if we're going to simplify it, we want to make sure that we still always see those valence electrons because that explains our chemistry.
Okay, so when we do the notation with the simplification of neon, we always go, like I was going to say you could just write it with just a 3p, but it has to be the entire 3 energy level.
It has to be the entire 3 energy level. All the stuff that's not explained by the noble gas that you chose.
Got it, okay.
Okay. Other questions with this? It might be more of a can of worms than I really want to get into, but let's do it anyway. What's up?
When you use X and Y, what time you use?
The only reason I used the PX, the PY, and the PZ was to specify that you had those 3 extra orientations. In this class, you will never have to use those. Okay? The only reason they were there is to specify that extra information and say we could add that extra stuff to it. That involves a lot of extra work on our part. Let's simplify it down to just the P's. Okay? Yeah.
So if we were doing bromine, do you have to use the noble gas right for it, or could we use the
So,
neon and then add the rest of them?
for bromine, what noble gas would we choose?
Argon?
Argon. Could we use neon? Yeah, why not? Well, the issue with using neon is that we would then have a complete full set of electrons getting us to krypton that aren't part of getting us to argon that aren't part of the valence shell. So it's not that it's wrong, it's that you did a whole lot more work than you had to do. So the idea is to minimize the work while still retaining the information. We're not going to do another one yet because we will see it again. So the big simplification that I really want to address with this, okay, is look at your periodic table. We saw energy level. The next big thing that we can pull from the periodic table is you notice it's not just a box all the way across. There's some shape associated with it. What are those shapes associated with? The electron configurations. The first 2 columns are always going to have in their valence shell s electrons, and only s electrons. So if I wanted the valence, or I wanted the electron configuration for, let's do barium. Okay, barium way down at the bottom of the periodic table. You can't look at the one on the blackboard for this, just so you know. You got to look at the walls, right? 56. We were going to do barium. We have how many electrons? 56 electrons. That's a lot of 1s2, 2s2, 2p6 stuff. So what we could go through and do is simplify. First off, go to the closest, the first preceding noble gas, which is what? Xenon takes us all the way down to row 1, 2, 3, 6. Okay, it gets us all the way through there. How many extra electrons do we need over the xenon configuration? 2 electrons. Starting in our 7th energy level. Is it 7? 1, 2, 6. I keep saying 6 and I keep not believing you. I apologize. Our 6th energy level, the first orbital in our 6th energy level, S, 2 electrons. Why 2? What's the first column? 1 electron. Second column? 2 electrons. Within the S. What happens now is that we've completely filled the S orbital within that class. So if I want to add more electrons, I would then jump to the p orbitals. Okay, which I know is a bit of a jump here because we're jumping all the way to 81. And we'd start putting in our p electrons. How many electrons fit into the p orbitals? 6. How many columns do we have in our p section? 1, 2, 3, 4, 5. Holy crap, 6. Okay. Within each of those sections of the periodic table, we're filling that orbital type. So our first 2 columns can be commonly referred to as the S block elements. Columns 13 to 18 are typically referred to as the P block. And that's because the last orbital filled is the P orbitals, or our S orbitals. What happens when we move to our transition metals? Now we're filling the D electrons. How many electrons can fit into a D orbital? Or how many orientations? Let's try that. How many orientations for the D? 5. How many electrons fit in each orbital? 2. 2 times 5 is? How many columns in our transition element section? Holy junk, there's 10. Okay? What happens when we move to our inner transition metals? How many columns do we have? I thought it was 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 columns within our transition elements. How many electrons can fit in an individual orbital? 2. So 14 divided by 2 gives us how many possible? 7 possible orientations for our F-type orbitals. Okay. With that, we only got up to how many different types? So we had S, P, D, F. Only 4 different energy levels. We said once we got up to the 7th energy level, we should have had 7 orbital types. Why do we not see those? Why do I not see a 5th energy level, or a 6th, or a 7th? Because now the atom is so massive, it can't hold on to electrons in those orbitals. Which means we can't find those elements. In theory, if we continue to make elements and continue to add electrons and protons together to make another element, we could move up into a new section of our periodic table, a new orbital type class. Okay? Thankfully, you don't have to worry about it, but maybe your kids will. Okay? Because physicists just do some stupid stuff. Okay? Stupid good stuff. Okay? So take advantage of the periodic table because you get a lot of information from it. Okay? What did we learn in chapter, what was it, 4? 4. What did we get out of the periodic table from chapter 4? Atomic number, our weight. I wasn't even thinking about radius, but we can bring radius into it. We saw radius trends with our periodic table. Okay? We've also now got orbital types for helping us determine our electron configurations based off of the periodic table. Okay? There's a ridiculous amount of information in here. If we bring it back to Mendeleev, okay, they started to group things excuse me, according to their chemistry. It's not helping. According to their individual chemistry, how they react with another molecule. Well, what did we just predict would interact first? If we bring our 2 atoms near each other, what's the first thing that interacts? The valence electrons. How are these organized? According to their chemistry first, but then we later found out their electron configurations match their chemical properties. Okay? So understanding something about the electron configuration can help you predict a lot of the overall chemistry behind what's happening behind these. It's enough behinds. Okay? Questions about that? Okay, 40, right? Next thing that we're going to use the periodic table to predict is something known as the ionization energy. Okay? It's a new term that we can introduce. It's defined as the energy required to remove an electron, technically in the gaseous state. So if we take an element and we say, okay, I want to pull that electron out of it, okay, should it increase in energy?
Yes.
Yeah, I'm taking an electron that's now attached to a stable nucleus or a stable atom. We're getting those charges kind of canceling out. It's becoming neutral. If I completely remove the electron from the atom, the electron energy goes up. So I have to put energy into my atom to get that electron out. Okay? That's what our ionization energy is measuring. The ability to completely remove that electron. In general, we can pick up some trends. Okay? Ionization increases as you go from the bottom to the top. Okay, well, does that make sense? Is it going to require more energy to remove an electron that is closer to the nucleus? Yeah. Why? Well, closer it is to nucleus, the more that charge is canceled out, the more stable it is. The more stable it is, lower energy. Okay? So the bigger our atom is, the easier it's going to be to remove that electron. We could go all the way back to those electron line diagrams that we were showing. The higher up we got, the closer we were to that vacuum. Okay? The next trend that we could look at is our ionization energy increases as we go from left to right across the period of elements. Okay? Does it make sense for that to happen? What's happening as we go from left to right?
More electrons.
We have more electrons. What else do we have? More protons. What's holding the electron there? The attractive force to the nucleus. So what happens as we move from left to right? We would expect that ionization energy to increase because there's more positive charge in the nucleus. More positive charge holding that electron in. Okay? Why does it seem counterintuitive to what happened with our atomic radius? Okay, with our atomic radius, it got bigger as we dropped down a column, right? Left to right, we said the atomic radius actually shrunk. Why would it shrink? Where are the electrons going as we move left to right? What happens to the energy level of the electron? Left to right? Stays the same. So we keep putting an electron in at the exact same energy level, but the nucleus is getting more and more positive. So what happens? It starts to hold that electron a little bit tighter, which means your radius decreases ever so slightly along the left to right axis. Okay? So our electron configurations actually allow us to understand a little bit more what's going on with our radius. Same thing's happening with our ionization energy. We typically expect it to increase as we move across because we're putting those electrons closer to the nucleus. As we move down the column, what's happening? Now we're increasing in energy levels. We're actually putting the electron further from the nucleus. That's going to cause it to be easier to be removed, also increase our size. Okay? Got to watch out for this one. In most of these, or in these two cases, and even with our radii, we say in general. Why do we say in general? Okay. It has to do with the electron configurations. Okay, so what we could do is jump to our ionization energy trend, and we can take a look at these. As we move from helium to neon to argon to krypton to xenon to radon, okay, where are those relative to each other on the periodic table? They're all noble gases. They're in the same column. What happens to the energy as we move down the column? It decreases. Why would it decrease? The electrons are further away from the nucleus. Okay, so our trend down in the column makes sense. As we move from left to right, so lithium to neon, what happens to our energy? It increases. Okay, and the reason we said was there's more energy or more protons, more positive charge in our nucleus. And our electrons are going in at the same effective distance, which means they're held a little bit tighter because they can't get further away. Okay? Is that trend true all the way through it? Does it always increase? Well, our first dot is lithium. What's our next dot? If we go up, lithium takes us to, so we add an electron, we go from lithium to,
Sodium.
that's not adding an electron. Lithium has 3 electrons, sodium has 11 electrons. That's not 1 electron addition.
So beryllium.
Goes to beryllium. So each of these vertical lines are representing in a row. Okay, so our next one is beryllium. Okay, what happens at the next ionization energy? Ooh, goes down for boron. Okay, and then it goes back up. Carbon, nitrogen. Then it drops back down for our oxygen before going up to our fluorine and our neon. Interesting. Why would that be the case? Why does it go down for boron and oxygen? What's the electron configuration for boron? How many electrons? I'm getting color happy. Sorry. Boron is B. We could go in, do all our electrons because it's relatively short. 1s2, 2s2, 2p1. If we compared that, say, to beryllium, beryllium is 1s2, 2s2. Why would boron decrease in energy? Why would that ionization energy be lower? Why is it easier to remove an electron from from boron than it is from beryllium?
Because beryllium has all the sublevel orbitals are full.
In beryllium, all of our energy levels are completely saturated. They're full. Okay, what happens when we get to boron? We have to add in this extra electron. That extra electron doesn't have any family. Okay, it doesn't have any friends. So what does it do? Because F this, I'm going to find somebody else. Okay? So it's relatively easy to remove that last electron because then we start to look like we have a full energy shell. Okay? What happens when we get to our neon, argon, krypton, and xenon? Why would they all be expected to have the highest energy? Well, what do their configurations look like? Oh, that's an awful lot of erasing. What's the electron configuration for, let's do helium. That's not helium. Let's do neon. We got 10 electrons that we got to put in there. So neon starts with our Ne, 1s2, 2s2, 2p6. Why would it require a lot of energy to remove that last electron? Because it started full. To remove that electron, now I'm not full. I'm not completely saturated. I'm not happy. Right? So it's going to require a decent amount of energy, more so than the others, to remove it, because we end up shifting into a non-symmetrical, non-balanced system. Okay? You should be able to show that for oxygen. What's our electron configuration for oxygen? Oxygen has how many electrons? If we fill it up, we start with oxygen equals 1s2. Should be 2p4 to get our 8 electrons. When we remove 1, it just becomes 2p3. Why is that a big deal? Not as obvious in this conformation, is it? So as Troy was asking, do we need those X, Y, and Z labels? Not really. But if we want to explain this ionization energy, instead of it being 2p4, it's 2px, 2py, 2pz. If we go through and fill our electrons, it would be 2px2, 2py1, 2pz1. Why would the energy drop so much? What happens when I remove that one electron? Half-filled orbitals. Completely symmetrical again. Okay? So we tend to strive for lower energy and high symmetry, okay, with a lot of things in nature. Okay? You can think about that the next time you think someone's attractive. Look at them, put up a plane around their nose, right down that line, and then see how symmetrical they are. Turns out the people that we find attractive happen to be very symmetrical. Okay? There's a few cases where there's one thing that's off. That slight asymmetry is enough to make them different. We say, oh yeah, now they're super attractive. But everything else is symmetrical. Kind of odd. Okay? It's what we're driven towards naturally. Chemistry is doing the same thing, balancing off of that symmetry. Yeah?
So why couldn't we do 2p2 previously
Always fill lowest energy first before pairing. Yep. Okay. What charge does the atom become when we remove an electron? It's always going to become positive. This is going to become relevant when we start to look at charges. So then the next thing, the textbook doesn't show this, and for a very good reason. It's easy to get confused, and the table I found didn't make it any easier to understand. One of the other concepts we can look at is something known as electron affinity. It's the energy released to pull an electron from the vacuum. So instead of removing an electron from the atom, Let's bring an electron into it. What happens in that energy release? The reason I address this is what charge does the atom become in that case? If it grabs an electron, its charge becomes negative. We've increased the amount of electrons now around it by 1 negative charge. Our atom becomes negatively charged. This becomes uber relevant when we look at, when we look at both of these. It becomes important because in both cases, what we're trying to do is get to something that looks like a noble gas. Okay, so what do I mean? Ionic charges. When we take a look at lithium, okay, it typically picks up a +1 charge. Why? If we drew out the electron configuration for lithium, what do we get? Lithium is, I'm going to be obnoxious with this, our electron configuration for helium plus 1 electron in the 2s orbital. Okay? Why are the noble gases cool? What was the other name for noble gases? Inert. They don't react. What does everything in chemistry strive to do? Become neutral, less reactive. Okay? So if we take a look at lithium, it wants to look like a noble gas. It could either look like helium by getting rid of an electron, or it could look like neon by adding 7 electrons. Which is easier? Looking like helium. Get rid of that 1 electron. What happens? Lithium becomes +1. What happens when we move across the periodic table? Say to nitrogen. Nitrogen could either look like helium by getting rid of, how many is that? 5 electrons, or accepting 3. Which is easier? Accepting 3. What happens? Nitrogen picks up a -3 charge. Okay? Because it's trying to look like the noble gases. Okay? We will come back to charges a whole bunch of times throughout the rest of the semester. You are going to be required to have some of these memorized. So start looking for patterns within this. A lot of it comes out of the electron configurations.